Good evening, participants. Today we are here with our third session on the Faculty Development Program of Innovation and Challenges of Energy Storage Technologies. And today we have with us Professor S.K. Singh from IIT BHU, and he will be delivering his experience with SiC-based charging technologies for the batteries. I would request Dr. Shailendra to please introduce our honorable speaker with the participants.
Thank you, sir. Thank you for the opportunity. And now, want to just so Dr. Santosh Kumar Singh received undergraduate degree in electrical engineering from M Engineering College, Gorakhpur, India in 2000. The master's degree in power electronics, electrical machine and drive from IIT Delhi, India in 2001. And the PhD degree from the Electrical Engineering Division, University of Cambridge, UK in 2011. For his PhD program, he was awarded a scholarship by the UK Commonwealth Scholarship Commission. His PhD work was focused on silicon carbide SiC-based inverter for hybrid electric vehicles. From 2002 to 2005, he was a lecturer in GCET, Greater Noida, India. Since 2005, he has been with the Indian Institute of Technology, BHU, Varanasi, India, and currently working as an associate professor in the Department of Electrical Engineering. He was more than he has more than 18 years of research experience. His research interests include power electronics topologies and their control, carbide converters. He has 77 publications in journals and conferences. He has guided 5 PhD research and 3 MTech guided research. He is awarded with a global patent. He has executed 9 sponsored working on research application portal, prospects of power converters for integration of electric vehicle charging systems with the existing electric distribution system in India, in collaboration with University of Warwick and University of Cambridge, UK. He's also working on a sponsored project entitled Design and Development of Cyber-Secured Smart Power Interface for Energy Local Area Network. Recently, he has started another project on smart DC charging with integrated digital platform for CPOs and power distribution companies. Dr. Singh is Associate Dean R&D at IIT BHU Varanasi. He is a senior member of IEEE, member IET, life member IEI India, and life member ISTE. He is a member of IEEE technical committees for Industrial Electronics Society, Power Electronics Society, and Industry Applications Society. He is an active reviewer of IEEE transaction in power electronics, IEEE transaction on industrial electronics, and Journal of Emerging Technologies. He chaired sessions in various IEEE conferences such as FEDES 2016, UPCon 2016, ECCE 2017, FEDES 2018, ITEC 2021, and STPEC 2021. In 2018, his research team was awarded with second prize paper award from IEEE Industry Application Society. So, with these words, I invite sir and I request all the participants please carefully listen his lecture, because now the era is of smart devices and sir has very vast experience in these SiC based devices. So because now we use these devices for electric vehicles as well as for charging purposes. Sir, please.
Okay, thank you, Dr. Shailendra. Should it be okay if I turn off my camera, or shall I keep it turned on?
Yes, sir, no issue.
Okay, so I'll just turn off my camera and then I'll start the presentation. Okay, so very good evening to all. And thank you, Dr. Sanjeev, Dr. Shailendra, for inviting me for this talk. The title, which I'm going to just share my experience with you, is silicon carbide based converters for energy storage applications. Since the title is quite, even the theme of this short-term course is quite nice, that the energy storage aspect is being seriously considered. So I will take up this concept, or rather, better to say that this theme, even in my talk. So I thought to start with very basic. Maybe few of the speakers might have just quickly gone through these things. So I'll just try to be on the surface, not too much detail, but a little bit. So since we are talking about the energy storage systems, we know what is the scenario of oil imports in India. And if we compare, this is slightly old slide because that has covered up to 2007. In this range, there may be slight enhancement in recent years. But broadly, if you look at the consumptions and the discoveries, you'll find that in our country, we are very much dependent on the import of this thing. And in recent, let's say, last few months, the situation that is happening in Europe, everybody knows what difficulty can happen if there is a serious energy crisis. So it's good that we should be prepared with it. Idea is not somewhat a very novel one. Just to highlight these old stories, you can see that these things have been, people have talked since around 100, even around 200 years back. Some people have tried with, let's say, electric vehicles, not exactly 200, but let's say 170, 180 years back. So it's not a completely new idea, and we can clearly see that there is there is some kind of changes that has occurred in this domain, but there was some gap in the beginning when there was a heavy kind of conflict in between the mechanical people saying that our IC engines are much better than your electric vehicles, and they really did well, and they got the market. And somewhere we were lost, though we started much early. So during this period, 1890 to 1910, that is a 20 years period, a lot of thing has happened on the battery side, because that was the weakest link, and still you will find that this is still the weakest link in electric vehicle. This is a very old patent that was filed long back. If you can see, it's 1902 story. So this patent was filed long back. So, but basically, if you look here, they are including the engines, they are including a motor, and they are including a battery. So whatever we are talking in terms of hybrid electric vehicles, people have already thought of those concepts long back, and still it could not be materialized. So certainly there was some reason, and even they have thought of some kind of engine and generator. So they were also thinking in terms of charging of the batteries at that time. You can just think 100 years back. So that story is an old story in a new kind of packaging. So this was a little bit about the old stories. And current day, if we talk about the energy storage systems broadly, we consider these storage elements, particularly for our electrical related applications. So batteries, we know it works on the electrochemical conversion principle. Ultra capacitors, they are supercapacitors. Some companies, they call it supercapacitors. They are storing the energy in that electrostatic form, and it's considered to be quite nice for high power density requirement. When we want to accelerate or retard the electric vehicle, then this ultra capacitors may be very useful. Apart from that, flywheels, they are mechanical in form, but sometimes back people did try it with this flywheel. But we know the problem is the weight and size of these flywheel. So somewhere it could not be converted, at least for the vehicle application. People could not think of this as a possible solution. But yeah, fuel cell is one another interesting aspect which government is also trying to push very hard with so many electrochemical. It's also kind of electrochemical energy conversion process. And right now, if you look around this situation in different countries, so there are lobby of companies promoting the hydrogen as a fuel cell as another alternative solution for vehicles. There are another set of lobbies which are who are promoting the batteries. So this is a very interesting case, and maybe they may find different specific application. Let's say battery may be useful for low and medium powered applications, and hydrogen may be a better solution for very high powered solution. Maybe that may come in coming time. Weight and volume of different tank types. The purpose of just highlighting this thing is when we are talking about vehicles, we have to consider how much kind of additional weight we are putting on the system, because it's a kind of moving system. So if you look at the gasoline or the IC engines, its weight is hardly 50 kgs and volume is, let's say, 70 liters. On the other side, if you consider the liquid hydrogen and commonly known as your fuel cells, you'll find that its mass is nearly equal to gasoline, but its volume is quite large, 190 liters. So this is one serious concern if you compare it with the IC engines, at least from the fuel cell aspect, that you should have a very kind of a bigger volume being occupied by this type of fuel. Because this is actually the best of all solutions. There is compressed hydrogen that has got more weight, more volume. Then you have got metal hydrides that are even more heavy, and their volume is also quite large. So out of all the possible solutions, this somewhat seems to be a better one. So this is about the fuel cell. That is one form of energy storage element. If we look in terms of the characteristics of various types of energy sources, let's say along the x-axis we have got this specific energy, that is unit is watt hours per kg, and this is our specific power along y-axis. So per kg is on that basis we are trying to normalize it. So you can see the ultra capacitors are lying somewhere here, and they have a very remarkable feature in terms of the specific power. It's very large, but their energy density is quite low. So they are not considered to be a good solution. They can just help the batteries to take up the additional stress that is going to directly fall onto the batteries. So the ultra capacitors can be just considered only along with the batteries or some other energy storage element like fuel cells. Then if we look into the flywheels, they are comparatively better in terms of energy density. Certainly that's coming better. The batteries, electrochemical batteries, their power density is further going down, and but at the same time their energy density is going up. So they are falling in this region. Uh, there may be some counter argument on this part, that which type of battery actually we are talking about. So there may be slight variation, but the range is going to fall in this region. Then we have, so up to this part, we can say it's kind of a rechargeable solution up to this section. And the region which is beyond this one, it is a non-rechargeable. So whether it's a IC engine with petrol or diesel, or it's a fuel cell, both of them are non-rechargeable. For fuel cell, which a number of companies are talking about, you'll find that energy density seems better than your batteries, but at the same time the power density is coming down. So whether you are using a battery or fuel cell, I think ultracapacitor needs to be placed in both the cases. Yeah, because of the requirement and the dynamics of those vehicles. If we compare the different type of energy storage systems, so we can have battery, ultracapacitor, fuel cell, flywheel. Let's say we have got these four options. And ultracapacitors, the beauty of the ultracapacitors is their charging time is in seconds. So as soon as there is a complete discharge, it takes seconds to quickly charge on. But again, the problem is with the energy density. So we have already talked about that one earlier. If we compare the efficiency, we'll find that ultra capacitors are trying to dominate among all others, but it is coming closer to your batteries. On the other side, your fuel cells, they have a very low efficiency. So that is a big trouble with the fuel cell. And even their volume is much larger. This may be useful only in very large vehicles and very large ship kind of propulsion systems where we want to put a larger volumes. If so, this efficiency is one serious problem, and these are some of the other characteristics which have been conveyed or communicated earlier. But yeah, certainly this ultracapacitor must be along with a battery or a fuel cell. Some of the recent, so this is what I have taken from some previous old slides, and now if we talk about the recent trends, so you will find that already this is a big trouble that we have around 13 cities which are considered to be the most polluted. So there are and Delhi is sitting at the top. So there are serious concern in respect of health issues in these cities. Apart from that, I've already mentioned about the oil imports. So there are some figures. So it's a huge investment that is being paid by India, by the country, just for importing oil. And this is slightly old figure. So you can think what's the current scenario, because every day the number of vehicles, even if you go on the road, you'll find more number of vehicles every day. So it's something like the number of vehicles are going up. And if we look in terms of lithium-ion battery solutions, so there is these lithium-ion batteries actually take around 50% of the cost of the total battery. So the thing is, people are quickly buying these vehicles. That's fine, but they have to think that let's say after 10 years or 15 years of lifetime of these batteries, so they need to replace it. So there is additional investment, though they are saving in terms of cost of the fuels, petrol and diesel, gasoline, etc. But basically, you have to pay at some other moment of time. So that's not going to completely go away. Even for the current day, they need to pay the electric bills, though it is okay because it is comparatively lower than your gasoline charges if you compare per kilometer. But still, it's quite significant. The most of these electric auto rickshaws, if you have seen, they generally rely on these lead acid batteries. So, and their life is hardly around 7 to 8 months. So that means there is a replacement that is required after 8 months or 9 months of time. And apart from the cost issues, we also need to understand that we are putting a heavy waste in the environment. How that thing is to be handled for, so the sustainability and other aspects should also be considered in terms of battery usage. uh, ISRO has taken a lead in this aspect because lithium-ion batteries, most of the time, it was being imported earlier. So they have tried to move forward, and they have look into this direction where commercialization can be done for the lithium-ion batteries in our country. Uh, if we compare, because there is some confusion sometimes that why we have directly jumped onto the electric vehicles and why not to the hybrid electric vehicles. So if we compare the data in respect of the years, so we have up to 2018, these numbers are there. And if we compare, and the green one, they are showing you the plug-in hybrids, and the blue ones are your battery electric vehicles. So you'll find that there is a more jump in kind of sales of these battery electric vehicles as compared to the rate at which these plug-in hybrid vehicles are being sold. So there are some figures who has actually influenced the policymakers to push electric vehicle in a better way. Uh, in terms of different other countries, this is slightly old one, but I don't think we are still in one of the leading numbers here, because we are struggling with the charging infrastructure issues at the moment. So if we compare the annual electric vehicles sales country wise, so we'll find that huge chunk is being taken by China. And even United States have got a very small piece of cake, and we are sitting somewhere among this rest of world section. So that's a very kind of negligible or a small number if we are looking, because we are one of the second most populated country in the world, but we don't have that much amount of stake in this electric mobility. So we can think of the fuel cell as one option and the batteries as the other option. But right now, I think fuel cell will take a longer time. Though I think NTPC is taking a lead in it, where they are trying to come up with their own hydrogen generating plants. But basically they are meant for larger vehicles. For smaller vehicles or medium powered vehicles, we are still relying on the batteries. So battery charging for these vehicles is where we have to very seriously think of. Now, battery charging cannot be done right now. What's happening is, wherever we are finding, let's say, a small the 3-point connectors, you'll find that a number of people are just plugging their electric these bikes around their home. But we since this number is less, so we are not getting that much amount of problem. But once the number is going to increase very quickly, then we have some impact that is going to come onto the distribution and transmission system of any city or any place. So some of the problems that needs to be addressed, one of them is that is transformer and line loading. So we know that wherever we are going to place these charges, we are injecting harmonics in the line. So if we are going to have more number of chargers, more is the harmonic content, though individually each one of them are contributing a little bit, but since their overall number is getting up, so the harmonic effects on these lines are getting increased. So on top of it, the transformers are a low frequency transformer. We know that these low frequency transformer, their insulation strength and the capability of providing isolation is designed for 50 years. Now what we are doing, we are putting some harmonics of higher order. So we have to think in terms of the life and aging of those transformers. Most of the time we do the core loss calculation, ED and hysteresis kind of losses based on 50 years. Now you have to do it for higher frequencies. You can think how much additional amount of losses or heat is going to happen in those transformers. So that is a very serious concern. Apart from that, if we have more number of charging points, and that too is going to be a variable in nature, because we have to think in terms of when, at what particular time people their vehicles in charging mode. Office hours, less number of vehicle, but during night hours, more number of vehicles. So that distribution network in particular is going to be heavily stressed with it. Power quality issues are another thing that is more related with harmonics. So that will certainly be there. You can't avoid it, even if okay, you can avoid it, but to some level by making use of some passive filters. But certainly those passive filters, nobody wants to unnecessarily spend a lot of thing on a very expensive charger. So that's another thing. Protection settings is one aspect. So protection settings, most of the time, these relays or the coordinated kind of protection scheme that is placed in the distribution network, they are more planned with the number of cycles in which they have to operate. Let's say if it is 20 milliseconds, so they have to operate in, let's say, 40 milliseconds, or 3 cycles, 60 milliseconds. That type of order is there. But if we are bringing down these charges, then they can start creating the protection setting, because the wrong signal is going to give them a wrong impression that some fault is happening, and actually it is coming from a spurious harmonic signal. So those losses will be there because of the harmonics which are present. People have tried to look into few solutions where they have tried to address the impact of these charging levels. And one interesting work was being reported, I think 2-3 years back, where they have tried to play around with the STATCOM in their distribution network. Generally, we consider STATCOM in the transmission network, but they have tried to put it in the Irish distribution network. And there was one kind of this is a single line diagram where they are showing that there are different nodes. So they have identified 1, 2, 3, 4, up to, let's say, 74 nodes. And they were trying to, and these are physical location of different houses. So each one of them have different numbers. So you can see around 7 to 8 houses are taking connection from one point. So that is PCC at this node, and likewise over here. So they have tried to play around with this thing in their study, and they figured out that there are two positions. One I would like to highlight. One is pillar J. That is the extreme. So their feed is coming from here. That is your substation, and they have tried to look into two different extreme situations. One is which is very close to the substation. The other is which is very far to the substation. Now they were trying to place this STATCOM somewhere in the network, and they have highlighted the pillar B and pillar J. So this one is the closest one, and this is the farthest one. So you can see they have looked in terms of the time axis, and then they were trying to look into the voltage in per unit. So with STATCOM, if we look, these dotted lines are with STATCOM, and these solid lines are without STATCOM. So without STATCOM, you can see the amount of dip. So let's say if we are considering the blue one over here, I think phase A. So that is dotted over here. So that is somewhat looking like this. And then without STATCOM phase A in per unit, so that is the yellow one. So if you just compare these two up to this duration for one phase, you'll find that with STATCOM, the voltage per unit is actually somewhat more as compared to without STATCOM. So this STATCOM is actually helping on the pillar J, but it is trying to create some over voltage at pillar B. So that is getting reflected here. So on the extreme side, you can also see that again, let's say this is our STATCOM phase A, which is dotted blue ones. So if we are monitoring it here, so we'll find that these dotted phase A, it is what we are trying to match with the unity voltage close to it. But without STATCOM, this is actually dipping too much. So STATCOM is actually helping the extreme ends, but on to the closer ends, it's creating some kind of over voltage situation. So that is going to create problem for transformers, because then you have to consider that wherever the location of those the points are being, sorry, the location of the STATCOM is there. So that is going to affect a kind of over voltage at the transformer, which is sitting close to the substation. So that's another interesting thing. Another part of this study was transformer loading. So if we just look at 11 kilowatts of charging with STATCOM and 11 kilowatts of charging without STATCOM. So this is the 11 kilowatts of charging with STATCOM. So you can see the transformer loading factor is getting increased up to 300%. Whereas without STATCOM, it's going up to 200%, something like that. So that means we can't just simply make use of the existing infrastructure. We have to do something else to consider that if we are putting more number of connections, then there may be transformer failures quite often in the distribution network if we are relying on the old infrastructure. So instead of STATCOM, people have also thought of, because STATCOM is going to create help at one point, but it's not helping at the other. So people thought of that. Some of the research group, they tried with some storage elements and renewables. So they are thinking that we can have a dedicated energy storage that is going to help to the EV charging station, and there may be some local power supply being generated by making use of the renewables. So people have tried some kind of concept, something like this, where these are the charging points, and behind the charging point you will find that there is a kind of a chamber which something looks like this. So this is the energy storage that they are offering closer to the charging station, that we can have a dedicated energy storage element there, and that is to be charged from either from utility or from the renewables. Both the options are open. So if we are doing it locally, let's say if you are just making use of the renewables, and we are not taking power from the utility, then it's so no worries regarding change in the existing infrastructure is there. So the problem is locally being solved at the charging station itself. So that's what is making these energy storage elements quite attractive. In a few of the concept, people are also talking about battery second life kind of concept, where they are saying that the automobile batteries, when their life is over, still it has got sufficient potential to act like, with slight improvements, to slight refurbishment, or what we, there is another term, but yeah, with slight modification and maintenance, they can just take that battery out of the automobile once its life is gone and make use it for kind of a grid energy storage possibility. So that second life concept is there. So that will bring down the cost, at least for the grid application, because there we are looking for a very large size of the batteries. So somewhere we have to make a trade-off. Then so in some of the concept, locally they are trying to place some kind of solar panels, and with the help of batteries, again the batteries is placed beneath this section within the structure itself. So that's going to help in the charging. So this idea of storage and renewables really looks quite nice, because then we have got a flexibility of not unnecessarily loading the utility as such. This is a similar kind of idea that was being done in Canada. So they are also making use of these solar panels, just like a shade on top of the automobile. So it's providing two things together, and they are making it. So the main purpose is not to impact the electric grid. That's the main theme of making use of these storage and renewables. Even in some of the places, they are just putting one single kind of charging points, and they have tried to place along with the battery storage within the city. So but this is one single pillar. There is not enough number of charging points there, but yeah, there is one parking area and then there is one charging node. So that's locally going to supply this particular one. And the second life concept that was also being done by in Germany. So there are those things. So okay, so talking about these things, we know that what kind of requirement is there and what is the impact of these charging stations. So broadly, if we classify these charging stations, so globally it has been classified in these three groups, and this is kind of onboard charges. Generally, we have in our cars this type of facility is already there. But if you see the power levels, it's not going beyond around 1.9 kilowatts or 2 kilowatts, something like that. So it's taking huge amount of time. That is, the charging time is around 11 to 36 hours if you are making use of slightly larger power level. So it's a huge amount of time. Nobody can wait till that amount of time. So the second option is, can we have some onboard chargers that are even more have more amount of power rating? Yeah, we can have. So but for home application, that's not possible, because generally the utility predefines this power rating of these residential buildings. But yeah, but for commercial uses, yeah, you can go up to around 19.2 kilowatts with a three-phase supply, which can push around 80 amps of current. That's the capability. And with that, the charging time is certainly going to come down. So this is somewhat related with the higher amount of power levels. And level 3, that is the fast one. This is what is supposed to okay. There may be some arguments, but if we say off-board DC charging, it's a very huge number. But mind it, let's say at some of the charging station, if we have 3 points, just similar like your petrol pumps, we can try to visualize a charging station, and overall it's consuming 150 kilowatts. But within the city, if we are going to make use of this kind of concept, you can think of there are huge number of population. So it's also equally going to stress the existing infrastructure. So we have to come out with some better solutions in that case. And these charging times are reduced much in this particular situation. These are few of the charging connectors, and in our country, basically we have adopted these 4 type of connectors. One of them is meant for AC. So this is AC connector, which is taken from the standard by the European countries. But for the DC, there is CHAdeMO, that is from Japan, then CCS1 and CCS2. So these are combo kind of charging connectors. The benefit of having a combo charging connector is you can have a combined possibility. That means you can make it work like AC charger, as well as you can also make it work like a DC charger. So one single connector can act both the ways. It depends on what mode of operation we want to select. So if you are looking for 3 kind of AC, you can rely on the 3 conductors, and then if you are looking for DC, you can rely on the bottom 2 terminals. So that concept is already there, and you'll find that there are companies who are already placing it around you. So that is there. But for us, we just need to understand that this is just a schematic of what is actually there in those connectors. So let's say we have the 3 lines, L1, L2, and L3. Then we have got a neutral. Okay. Then we have got one P, that is a protective earthing wire that is sitting in the middle. So that earthing wire is playing a very important role, because anything goes wrong, it is going to quickly bypass the thing, and then the protection is going to act together. Then we have some control signals that is being taken care by 2 commands, that is PP, that is known as proximity pilot. This will just make sure that the vehicle is close to the charging point and it's well connected, things like that. So that just confirms this part, that is physical position of the vehicle. And CP is a control pilot, that will take care of some kind of information, that what is the state of charge of the battery. So the charging station needs some information to be taken from the batteries, and this is what is done by making use of these control pilots. So control pilots, these are low level signals. They will just sense the amount of SOC and then communicate. Nowadays we are talking about SOH as well. So they will just convert those signals and communicate. So they are meant for communication. This PP and CP, this is actually meant for communication part. This is a typical figure for a supply station and the vehicle. So if you look, the supply station has got two parts, your charging point. So these two are what are the important things. And on the vehicle also, we have two blocks. One is our battery, that is the energy storage, and the second is the communication. So that suggests us that wherever we are thinking about placing the energy storage elements, we should start thinking of integrating communication block in the same module, rather than thinking of separately placing it. We can have the communication module well integrated with these power modules. So there are a few protection schemes which are placed in this one. So it is very much required to monitor the isolation, whether there is some problem with the cables because of overheating, etc. The cables may burnt out or the insulation damage may start happening. So isolation must be monitored carefully. That is monitored by some fixed amount of initial voltage that is given to the vehicle, and then they sense whether the voltage is going to be the terminal voltage is not actually falling. So it's not falling within certain level. So it's everything is fine. Then there is some temperature measurement that is also being done to ensure that the overheating is not happening. And I have already mentioned about these two pilots that is meant for communication. The CP and the PP, this thing is there. And then we have some other P kind of nodes, that is a low level of communication that is required in between the station and the vehicle. Now, talking about the battery charging, this is somewhat a very simple slide where we need to understand that for slow and moderate DC charges, let's say around 3.7 kilowatts and more, we can make use of either a single phase PWM rectifier along with a buck boost, or we can have an interleaving to keep an eye on the power factor. So for that purpose, we are placing one single phase PWM rectifier. Diode rectifier is not recommended. And we can either go for buck boost or interleaved buck boost. That depends on the current loading that we need to draw. Though it is 3.7 kilowatt, but you also have to think in terms of what voltage we are looking here. If the voltage rating is, let's say, 24 volts or 48 volts. So 48 volts will mean that basically the amount of current is going to be quite large. So rather than having one a single inductor, it's better to have an interleaved configuration. So if you are trying to charge a low voltage batteries, we can have an interleaving option. If you are going for a high voltage battery, then okay, high voltage means still higher than 48 volts up to some level, then the requirement of interleaving may be somewhat reduced. So the size of the inductor actually directly decides how much is going to be the volume being occupied by the converter. So if you are going with the interleaving option, then we can have more number of inductors of smaller sizes. So that's going to give us a comparatively compact structure as compared to one single inductor of very large current rating. For 15 kilowatt and more, there is a very set standard practice which companies are adopting, where they are making use of three-phase PWM boost rectifier, or sometimes they also make use of some interleaving there. So there may be interleaving in this section as well. Onto this side, that is your DC to DC. So this is converting AC to DC, and then the second stage is DC to DC. So there, this full bridge converter or dual active bridge converter is quite popular in the market, and based on this, further some LLC resonant converter were also being proposed, and they are working, but they are considered to be better for very large power levels. This is one schematic that is just highlighting the requirement at a system level. So let's say we have to charge a high voltage battery. So apart from the physical charging point, there are a number of sensors that are required to make sure that the voltage is quite intact. So you need a number of sensors at this level. So let's say we have ADCs coming out from this level, and at the same time we are sensing, putting all these isolated, these must be isolated signals. You have a two level of isolation. One is the power level isolation, the other is the low level, that is logic level isolation. So this should also be there. So a number of sensors are actually required. We need to sense the current from different. In this structure, they are making use of four-phase interleaved PFC as the first stage. Then we have a full bridge driver circuit, and combining. So this is our interleaved PFC. Okay. So we have to control all these MOSFETs. So we need to sense the current, and we have so many number of sensors. So interleaving requires so many number of the microcontroller to accordingly generate the gate drive signals. Plus, we also need to take into account the DC, the current that is sensed from the AC side, the voltage that is sensed from this side. So we have a lot of arrangement to be done here. Apart from that, we have some power line communication, that is where we are making use of the same 50 hertz supply, and then we are just putting some kind of high frequency communication, low voltage signals on top of it to communicate it with the charging station with the vehicle. So that PLC is also required, and we have a number of interfaces. So it's not that we are just relying on one or two modules. We have a complete system, and for one single battery storage, we have to consider all of them together. Now, the state-of-the-art DC fast chargers, because we have a higher rating of these chargers. So it is considered that at this power level, we cannot think of kind of bidirectional converters, because the power level is quite large. So the moment we start feeding this power back into the distribution network, there may be a situation like over voltage and protection tripping. So at that power level, it is suppose that VNR rectifier can be a better solution. VNR rectifier is kind of a unidirectional rectifier. It consists of two stages. One is the rectification unit, the other is the power factor correction unit. So the two together gets embedded or integrated within the same type of rectifier. And further, we can have some DC to DC isolated full bridge. This is quite similar like your DAB, except that there are some capacitors that are purposely being placed in this circuit, so that your DC saturation issues may be avoided. That's a huge power level, so saturation may happen. So that is one additional precaution that is kept. So this is our state of the art, and we have both input and output filters. So they are integrated part of it. Some of the concepts which are there in terms of charging stations. One concept is where people are talking about AC coupled system. So let's say if you have a medium voltage grid, and then we are making use of some kind of low frequency transformer. So that is your medium voltage. Uh, that is medium voltage. Just 1 minute, I'm getting a phone call. I'll just come back within a second. हेलो. हाँ, अभी थोड़ा एक टॉक से मैं फ्री होके आपसे बात करूं. एक टॉक में हूँ इस समय. हाँ, ठीक ठीक, ओके. Sorry about it. So low frequency transformer is one possible solution. So we can have that type of AC coupling everywhere in our connection, and then we need so many numbers of AC to DC converters to ensure that uh, we have to keep this AC bus stiff. Even the renewable which is trying to feed it, or the energy storage that is trying to feed the same AC coupling, they have to convert this DC supply back into AC. So whether it's an AC to DC conversion for charging purpose, or DC to AC conversion when we are trying to take this renewables onto the AC coupling, that's increasing the number of stages. So what we can find that in this kind of approach, the converter technology is very much matured, because AC converters are people are already using it. Even switchgear and protection for AC supply system is existing. We have a very set standard and practices. So for AC distribution, there is no problem as such. But we are directly finding that more number of conversion stages, so the efficiency is getting reduced, and the complexity is increasing. Complexity, particularly in terms of complexity, is that the control issues. Everywhere we need to just synchronize all those elements in the same AC network. So we have some control issues that we have to consider in this AC coupling. Likewise, we have a DC coupled system where instead of having an AC coupling, we can put a bigger rectifier in the first stage, and then we have everything in the form of a DC. So it looks comparatively better than your AC coupled system, because now let's say if you have a 800 volts DC line, and then you are trying to take everything without making use of any DC to AC or AC to DC conversion. So that is done centrally at one place, and throughout this architecture, it is a stiff DC. The positive thing is certainly we are reducing the number of conversion stages, and it is also simplifying our integration of the renewables and PV. We don't need to bother or please about the synchronization issues. The problem with the DC is the switchgear and protection devices. Though HVDC is there, but again, that is at a very much higher level. At this power level, that part has not been taken up earlier at the distribution network. So that is one limitation where companies are already looking into. Then onto this part, I think the Indian this our standard society is already working on that part as well. So this is what is still under discussions are going on, and we hope some draft is or elementary draft has just been communicated. I'm not sure, but that thing is just coming out. Another concept which is very fascinating, and a number of researchers are working on it, is to make use of solid state transformers. So in solid state transformer, they are just avoiding the low frequency transformer at this stage, and they are making use of some solid state high frequency transformer to justify that the size of these transformer can be made very much reduced. So the size will come down, and that will so instead of having a very big low frequency transformer, its size can be as large as like a briefcase. You can bring it in and then connect it, and that's it. So but at this moment I'll say that one serious problem with these type of SSTs are their efficiency is not uh, as good as our low frequency transformer. So though here we are saying it's higher efficiency, but this higher efficiency is when we are considering other factors into account. Okay, but this is not in terms of comparing one component as such. So the proposal is that we can have some wide band gap devices that will try to reduce the size of these converters. They can also offer better efficiency, but this efficiency is coming because of WBG devices. Okay, so that thing is where people are saying that with the WBG wide band gap devices, you can bring down the losses in the converter. But again, the problem is once you're replacing a passive transformer with an active transformer, you have to be very careful that there are more number of components, and so the reliability will get reduced. The more the number of components, the lesser is the reliability. Another issue is the inertia in the power distribution system is large. So if it is large, then we cannot actually quickly damp out all the issues related with the distribution network so easily. So even if you have a very fast acting converter, but there is a lot of inertia in the distribution network, so we are not able to make use of it. Then a requirement of one additional communication and control. So I think the power system people have already they are talking about this additional layers for a number of years. So even at the transmission level, that's already there. But in distribution network, with the smart metering and those concepts coming in a realistic scenario, these communication protocols are now there in the market. This is one fast charging station architecture, and this is the existing one Tesla 675 kilowatt supercharger station, and they are making use of 135 kilowatts of 5 units. So it's coming out to be 675 kilowatt. But this is a low frequency transformer, and this is our conventional switchgear and metering units. So typical efficiency is around 92% for this particular. And this is our estimated values for a new station. In the bottom one, it is expected that we can have some, let's say, medium voltage metering. Then we have some switchgear, so that will certainly be required. But at this level, they are making use of solid state transformer. So this is three-phase SST of around 2700 kilowatt. Then a DC bus bar. Then we have around 3 to 4 times more number of charging points. So some DC convert. So overall, this is minded. This is an estimated number. I will not say that this is finalized. This is just based on some certain study that we'll be able to get more efficiency with within the same area. Now the footprint is the same. Footprint is, that means whatever dimension that is being occupied by this supercharging station of 675 kilowatt is the same dimension being occupied by 2700 kilowatt SST based MV medium voltage charging station. So fast charging station. So this fast charging architecture is one area where we can try to push the SST concept, and that too along with the wide band gap devices. So this fast charging station architecture, if we compare, so what we'll find is existing transformer and charger. So it's around 93%. So this is getting increased up to 97%. Volume is actually getting reduced. So this service transformer is so big, and with the same concept. So this is the existing one. You have a service transformer, then you have an EV charger. But the futuristic proposal is we can have SSTs, and the size of these things are going to get reduced by order of difference, let's say around 30 times of volume reduction. And cost is also supposed to be reduced, that too because we are avoiding the low frequency transformer. In all these low frequency transformers, there is a conductor that is supposed to take care of whole of the current. So those conductor cost a lot. And then too, you have to consider the cooling and the protection units over here. So that's much expensive. So this is what is considered as a futuristic solution. And yeah, in coming time, we can find it. Now, one important component which I have highlighted in my previous slides is the dual active bridge, which sometimes may also be used like LLC by placing one more capacitor. But broadly, we in a dual active bridge is a very important component of this charging stations. And the working of this dual active bridge is dependent upon the phase shift that we generally, you might have seen this kind of isolated structure with a high frequency transformer. So we say it's a DC to DC converter. But in this case, what is proposed is generally what we do is we switch on these two, and then we switch on these two, and simultaneously we switch on the corresponding switches, so that the power can be transferred from one level to the next one. But when we are considering the phase shift, so that is the beauty of this dual active bridge, that the G1 and G3, these two legs, are there is a relatively a phase shift that is being created in between these two sets of legs of the converter. And this is just an equivalent circuit that is trying to highlight that these two voltages are very important for power transfer. So one is our input voltage, that is again a kind of square wave, and our output voltage is also VCD over here, that is referred onto the primary side. So that becomes VCD dash. So this is one equivalent circuit representation of this dual active bridge, and we generally make use of this one for doing all sort of calculations. The beauty of this dual active bridge converter is its power density is quite nice as compared to the other solution. I haven't touched upon other ones, but yeah, has got better power density. Both buck boost capabilities are possible. Device stress is much less as compared to the other possibilities, because the devices have to be rated directly in respect of these voltages with slight amount of leakage inductance that need to be considered. But primarily it is all about the lower amount of device stress. Small filtering component. So we are working at higher switching frequencies. So with the higher switching frequencies, our filtering requirement will also come down. So that filtering requirement will reduce the size of these filters. Then modular structure, I must emphasize that modular structure is a very nice feature of these dual active bridges, where if you want to enhance the rating of the converter, or if you want to take it into the maintenance and repair kind of thing, you don't need to do a lot of things together. You can simply take out one stack and put the other stack inside, and things can start working. So that modular structure is another beauty of it. There are a few modulation schemes. I'll not go much in detail, but primarily we have single phase shift, where we are making use of phase shift variable in between the primary and the secondary. The second is extended phase shift, where we are extending the phase shift. So we have a phase shift in between primary and secondary, and then we are making zero voltage level also being integrated within this network, onto the primary side. So you will find that apart from positive and negative levels, we are also trying to put another level with extended phase shift on the primary side. Then dual phase shift is something where you are putting a kind of zero levels both on the primary side as well as on the secondary side. Now, placing a zero level actually helps us in soft switching. So if we are trying to bring down the kind of, let's say, if these diodes are conducting, let's say if I'm saying that let's say G1 is closed and the current is flowing something like this, and if I'm not switching on G2, I am left with only one path, that is through diode this is conducting. So this is bringing down one zero level. Now during this period, if across this particular G2 switch, effectively we are getting zero voltage. So we can switch it on quickly to get a zero voltage switching scheme. So soft switching can be integrated by making use of that zero voltage integration state or zero voltage levels. So that's what has been shown here. Dual phase shift, then triple phase shift can also be done where we bring down. So this phase shift is for G1 and G3. Likewise, we can also create one phase shift in between G2 and G4. So that will create another level of control on the power flow. So these are few of the, then we have triangular current modulation, trapezoidal current modulation. These are few of the modulation techniques. So these are directly based on phase shift. These are based on nature of the current that is flowing through the transformer. So that actually should fall in a different category, but right now I have just shown it at one place. So for single phase shift modulation, I'll not go much in detail, but we have a very limited region for soft switching. You can see that if we are referring to this VAB or VCD, so this transition is taking place very quickly. Nowhere we are getting a zero voltage. So there is a very limited region, and that too is going to happen only by zero current switching. So we have to sense the zero current instant, and then only we are going to apply the soft switching. So the range is very limited, and we rely only on the phase shift of the control variables. The problem with this one is there is some circulating current issues because because of a kind of hard switching, we have some duration when the circulating current starts flowing through the devices. We have not integrated the zero level, so diodes are not coming. We have to provide alternative path either through this switches or through these switches. And because of the presence of circulating current, conduction losses also gets increased. Then we have an extended phase shift. I have already mentioned about this thing. So you can see that there is a presence of kind of zero voltage, this VAB. So this is coming onto the one of the voltage VAB over here. So this is creating a zero voltage level. Okay, so we can create soft switching only on the primary side, not on the secondary, because secondary is jumping from minus VD to plus VD, minus V1 to minus V2 to plus V2. So it's not taking place quickly, and it can also be linked with the slope of the current. So you can see if it is jumping from 0 to V1, the slope is getting reduced. If it is the slope is getting reduced here. The slope is getting reduced, and then we are saying that the effect of this one is coming, so that will help actually bring down more slope of the current. So these are few points, and in this case ZVS is possible. That is the main thing, that ZVS is possible, and we have two control variables. One is the phase shift, obviously, and then duty ratio is another thing. Circulating current will also be lower in this case because we are making use of the zero levels. So circulating current are getting reduced, and so is the better efficiency. Then dual phase shift. In this case, you'll find that this zero levels is shown both at the input side as well as on the secondary side. So both primary and secondary, both of them are have some amount of zero levels, and this is creating one more control variables, that is D1 and D2. So at the same time, we are getting soft switching both on the primary side as well as on the secondary side. So yeah, these are the ZVS is possible. So wider range than your extended one, and circulating current is further getting reduced. The peak value, we are reflecting to the peak value because we are able to control the slope of this current by injecting this zero levels. So that is bringing down the currents. Then triple phase shift modulation. In this case, there is another variable. So we are seeing D1, D2 is already there. Then we are bringing down this D3. So relatively, there is some kind of a duty ratio, phase shift ratio in between these two duration. So that will further reduce this quantity. So phase shift ratio is different, and zero voltage is obviously possible in both of them. Now we are getting three control variables, D1, D2, and 5. Both all these three are there. Then for triangular current modulation, I'm just bit because time is running out, so I'll be more quicker. Here we try to make use of the ZCS concept. Basically, earlier we are trying to make use of the ZVS. Here by controlling the current and making sure that it's just following a triangular pattern, we can create a zero crossing point. So during this period, the zero current switching is possible. That is the main beauty of this one. So in this case also, zero voltage is certainly there. At the same time, we are also getting the benefit of zero current. Yeah, both zero voltage and zero current. Okay. So these are few of the points, and in our group we are working in this one. So there are few simulation results in respect of single phase shift, extended phase shift. So you can see extended phase shift has been done here. Then we have a dual phase shift where we are bringing down the phase shift not only in one level but in both the levels. So your voltage, this levels are getting zeros, and in triple phase shift we have more number of variables. So we are already working in this area in our group. Now, yeah, so energy storage in electric vehicles. Okay, yeah, so some lights I'm placing here. Why? Because it's not that these charging of the batteries are only required at charging station. They are also required at different levels within the vehicle. So this is one model of Honda Civic, that is a hybrid vehicle, and you'll find that this is based on a fuel cell. So fuel cell, they are placing some kind of hydrogen tanks, storage tanks over here, and they are combining the concept of hydrogen storage tanks, and along with it we have some batteries. So it's not that we are completely relying on one energy source. So there is hybridization of these two things together. So fuel cell stack, that is taking care of this hydrogen. So it is converting that hydrogen in form of energy, and then they are trying to drive this electric motor. So they are making use of both of the concepts together. This is one figure from a company called Prius. Here they are placing this modular inverter along with some capacitors, and these are the connecting terminals. Uh, they have some power modules that's not visible right from this point, but yeah, we have some motor terminals coming out and some buck boost converter that is acting like a transformer, not transformer exactly, but yeah, it's trying to take the levels different. So we have some high voltage battery connection there. In this case, Price has not taken the fuel cells, but they are just relying on the batteries. And Toyota has further taken another model. They have tried to combine various levels. So this is our inverter circuitry. Some IPM section is there. This is our boost converter. So the bottom one is our inverter section. The top one is a boost converter that tries to lift the voltage up. And there are a number of DC link capacitors over here. And then there are some cold plates to keep the devices cool. So that is actually there. This kind of concept is there, but I'm not sure whether it's matched. It's going to be converted in realistic case or not. But yeah, people are also just like Prius tried with hydrogen that cylinder, but the size and the weight is going to create some issues. So there may be two options. We can have high voltage rating of the fuel cell and the low voltage rating of the batteries. And this is typically a 20 kilowatt converter. And so the remaining 100 out of 100 kilowatt inverter, we can say it's 20 kilowatt. The remaining is to be supplied by the fuel cell. So 80-20 ratio is distributed in between in terms of power rating. But fuel cells would be required to be connected with the DC link capacitor. So that's around 380 volts of range. So this is a high voltage fuel cell and a low voltage battery. That is one architecture that is possible. The other architecture is when your low voltage battery is it's acting like along with a high voltage battery. So that is another possibility. So we can have some low voltage battery that are going to support to the high voltage batteries, and there may be some ratio of 80-20 over here. So your high voltage batteries, where we are connecting number of cells together in series, they are contributing to the 20% part, and the remaining part is taken care by this low voltage battery. Yeah, so that kind of different architecture people are already working with. Now, coming back to the first important point of this silicon carbide converters, which is the title of this talk as well. I'll just go back to this slide. Let's say, yeah. So let's say if we have this size of the converter, and we need to keep it cool, we have to maintain the temperature. So there may be one option that we can place some kind of coolant, additional cooling unit, a bigger size of the heat sinks, or we can make use of the same, let's say some kind of generally in all these vehicles we have some coolant, so that is required to keep different things cool. Even your air conditioners, we have some coolant. So we can make use of some sections and try to utilize these heat management or heat sinks, or better to say, in our work, we actually, what we did was we were working on HEVs, and we are making use of the radiator, that section, in the form of a heat sink. So we pasted all the devices directly on the radiator unit, which actually works at 100 degrees Celsius. So that's what we did. So basically, the purpose of we have these converters. They are working fine, but the thing is, can we think of further miniaturizing these converters so that the space that is left by these additional converters or by these converters may further be used for placing additional energy storage element? Because the anxiety of these rides, a number of times these EVs, people talk about driving distance anxiety, that how long the ride is possible. So we can think about some possibility in terms of silicon carbide converters. So one thing which comes to our mind is, why not we can just live with the silicon? What is the problem with the silicon? So the biggest problem with the silicon is their maximum junction temperature. So if you're exceeding beyond, let's say, this value, this is good for high powered devices, that is power electronic devices. For actually safety margin, because we have a higher thermal cycles. So in these thermal cycles, there is a wide variation of the junction temperature. So we cannot try to hit, we have to keep a safety margin. So for power electronic devices, it's around 125 degrees Celsius. So that is one serious limitation. Apart from that, conduction and switching losses are there. Then there is some EMI related problems. We also need some extra cooling devices because we want to make sure that the junction temperature should not exceed beyond this value. So broadly, we can say that if we are making use of the silicon, then we need to compromise in weight, we need to compromise in size as well as in efficiency. So what is the alternative solution? So the alternative solution is we can think in terms of newly developed devices that falls in the category of wide bandgap power devices. Again, I will try to emphasize that the wide bandgap, this is not a new thing. Okay, mind it. People have already worked with wide bandgap, not as a semiconductor devices, but yeah, in other applications they have already made use of these kind of SiCs, and as an insulating material also, they try to make use of it. So with the wide band gap devices, obviously as the name suggests, band gap is wide, so the breakdown voltage is higher. And if the breakdown voltage is higher, then we can put more impurities in it, because you'll find that the drift layer in a device is actually responsible for blocking the voltage. So there are 2-3 layers. Among them, one is depletion, then drift. So that drift layer, that is the N minus, which is generally mentioned, of lower concentration, that blocks most amount of voltage. So if you have this type of device, then you can bring down if you're saying my concentration is the same, then you don't need to just 1 minute. Sorry for that. So basically, if we are considering the same, let's say, wide bandgap material, then we have more amount of breakdown voltage, and we can reduce the on-state resistance by putting more amount of doping. Because we have margin in which we can doping means your impurities or other materials which are being placed inside the device, some kind of charges. So if you are putting high or you are increasing the concentration of the drift layer, so its on state resistance will come down. So that is another beauty of this wide band gap power device. And thermal conductivity is really nice, particularly for SiC, mind it. SiC, very nice thermal conductivity. And theoretically, it is expected it can go up to 600 degrees Celsius. So there are more chances that we can push more amount of current, even in this, if the current, or you may say the chip size is same. Excellent reverse recovery characteristics, because the amount of reverse recovery is commonly being seen by the storage of charge in any power device. Now here we have got more amount of impurities, so sometimes we place some implants inside the devices so that the switching becomes more fast. At the same time, it also helps in the reverse recovery phenomena, so that it actually reduces the EMI. So what are the possible solutions in this group? We generally say silicon carbide, gallium nitride, or the best is considered to be diamond. But for the diamond, we know what is the problem. Everybody is aware of the cost of the diamond, and the technology knows it very well that diamond is one of the hardest materials. So having or processing that kind of material, your manufacturing cost will also go tremendously very high. On the other side, these are comparatively lesser. They are also hard. At least SiC is a hard material, I must say, but it's not as hard as like diamond. So we have got nearly similar amount of band gap, both in the case of silicon carbide as well as gallium nitride. In one of the work in Oak Lab, they have actually tried with some kind of theoretical work. They tried to estimate the size of the silicon and the wide band gap. So the yellow ones are showing the wide band gap, and the blue ones are the silicon. So you can see that if you are looking in terms of the rating of the switch current, and then you have a die area along this axis. So what is happening is there is a big, huge gap in the chip area. Now, what benefit are we going to make out of it? So it implies that, let's say, if you have a die means the die is where you grow up all the wafers and then you develop the devices. So generally, they have a fixed kind of dimensions. So if you can have this WB devices, so you can get more number of devices out of the similar size of the die. So rather than, let's say, if you are saying 10 times of difference, order of difference, you are gaining 10 times. That is, for silicon, if you are making 1,000 chips or 1,000 devices, with SiC you can have or GaN you can have 10,000 devices, nearly 10 times. So overall your cost is going to come down, and that's what you may have seen in recent years, that these devices cost are tremendously coming down. Now, one common thought which comes to our mind is, which one is better? Shall we go ahead with SiC or shall we go ahead with GaN? So I'll say that just keep a thumb rule. GaN, because of the better mobility, charge mobility, GaN is better for high switching frequency application. When we say high switching frequency application, you have to think in terms of megahertz. Mind it, it is trying to go into that range where we are justifying of the order of megahertz of frequency. And if we are looking for high power density applications, I'll just come in a moment, but SiC have a tremendous thermal conductivity. Now, thermal conductivity, if it is good, then the device has a capability to cool down much quickly. At least it's 3 times higher than GaN. So for high power rating devices, it is considered that SiC is a better solution. For low powered but high frequency application, it is considered that GaN is a better solution. So there is some kind of trade-off. We have to understand which one is better in which section. We can't just keep the GaN as a better candidate for high power applications. So SiC is better in terms of its power density is better. Now, power density, one common term is power density. What is power density? That is power per unit volume. So per unit volume, that's what we say. And what are the important factors that define the volume of a converter? So there are two factors. One is the passive filters, and the other is the heat management unit. So these two actually decides how much should be the what kind of the volume of the converter. Now, with the GaN, the benefit is you can reduce the size of the passive filters. With the SiC, the benefit is you can reduce the size of the heat management unit or heat sinks. So they have their own benefits, and we can't say that each one is we can arbitrarily use any of them anywhere. It's not like that. Now, just I mentioned about high power density. I was just thinking to give a difference in between these two terms. Quite often we talk about high efficiency, and blindly we say that whatever work I've done, it's highly efficient. But we have to understand that these technical terms have their own relevance at different places. So if we say high efficiency, this is good for static application. That means something which is not in motion, something which is not moving at all. If it is static, you can have high efficiency. But something which is sitting in a corner, you can have high efficiency, but you are not bothered about its weight, about its volume, because you know there is sufficient space in the building. But if there is a moving application, then the power density must be high. Why? Because it is this moving application has static losses, that means switching and conduction losses. At the same time, there is some amount of dynamic losses. Dynamic losses implies that because of the weight of the converter, whatever losses are coming because of mechanical units, etc. So that is going to counteract, and that will also contribute to my losses. So we better look for high power density high power density converters for moving application. Let's say electric vehicle. We are looking for high power density. Efficiency should be high, but broadly we say power density. Don't forget about power density. There are certain challenges since time is running out, but that is more related to the material people. We know that it's very quite hard material, so processing it is not so simple. And another problem is about the packaging of these devices. So particularly with SiC, I'll say, because we work with SiC for quite a long time, and SiC has got a very nice feature of better thermal conductivity. Theoretically, it looks very nice, but are we actually making use of it? Let's say if I am putting a very nice material having very nice capability of releasing the heat, but on top of it I am putting a very bad blanket or package. So what's going to happen? The chip is trying to release the heat quickly, but there is no one who can take out the heat so quickly. So the problem is going to come when there is a thermal issues, and within the chip there may be a situation that what we call thermal runaway situation, where the internal temperature of those chips are building up. So that is a very serious problem. And you will find that even in we also place order from different companies like Cree or Infineon for these devices, but they are making use of the same conventional package. Still, it's the old package of those lead-free kind of packaging, which TO220 or TO247 kind of packaging they are making use. So that's a very nice chip, but if you're not putting a good package, then everything is gone. So we should be careful with it, whether we are actually exploiting the potential of those devices or not. So gold is actually the best solution, but we know very expensive. Then people have tried with copper, but then copper with the problem is it's not very ductile. It actually creates some kind of cracks in the package. So aluminum is right now being considered as a better solution. Apart from that, some of the companies, they are also trying with some different possibilities. This is the first type of device that came into the market, that is SiC diodes. And the power factor, this PFC circuit manufacturing companies, they are hugely making use of the Schottky diode. This Schottky diode is a type of diode which has got metal and semiconductor junction. So this does not have a PN junction. And if you don't have a PN junction, then no reverse recovery at all. So that's possible with the SiC Schottky diode. And why there are actually silicon Schottky diodes also, but you will not find it beyond 100 volts. At most, silicon Schottky diodes are available up to 100 volts. But SiC Schottky diodes, you may go up to 800 volts or so. So that's going to serve the purpose of so many consumer electronics. So because there is no reverse recovery, the EMI is quite low. And in some of the study, people have tried to make use of these Schottky diodes. When they try to place it across, they simply, in a normal three-phase inverter, you have a switch and then parallel to it is a diode. So what they did, make use of silicon IGBT, and then parallel to it, simply place some SiC Schottky diodes. And surprisingly, they were able to get around 10% of reduction in the losses. So that too happened only at 10 kilohertz, because they were looking for motor drive application. So apart from diodes, there are control transistors also. There are MOSFETs. The problem with the MOSFET is its transconductance. It has low transconductance. Now, transconductance, if very quickly I can just tell you that there are different modes of operation of a MOSFET. So If you are switching from the on to off to on mode, uh, if the switching is not fast enough, then there is a possibility that sometimes we are spending time in the saturation region. So with the this type of SiC MOSFETs, there are more chances that huge losses can happen in that region, saturation region. So there are some dedicated, we must have a very aggressive gate driver that's taking it very quickly from one mode to another mode. Then only we are going to make use of it. If we are slowing it down, huge losses will come inside the device. And that's commonly happening at a number of places. No gate oxide for JFET. This is another type of transistor. That's what we call as junction field effect transistor. The initial devices, people actually tried with MOSFET, but there were a lot of problems. So they also tried with some other devices. Actually, I work with these JFET. So, but nowadays these JFETs are okay. Companies are providing it, but since you have got the MOSFET, so it's better to go ahead with the MOSFET. With the JFET, the main biggest problem is it's a normally on JFET. Okay, so this is one typical structure of your SiC JFET. So even if you don't give any signal in between gate and source, it quickly the current starts flowing from drain to source because no depletion gets formed here. In order to keep it off, these JFETs were uh, placed in series with a MOSFET. This is a silicon MOSFET, that is a low voltage silicon MOSFET. And by making use of these two, we can control the switching of the SiC JFET. So this is our normally on SiC JFET, and it may be operated because if you are bypassing this one, this is actually one device that came from Infineon, SiChed, now part of Infineon. So it is a 4-terminal device, and they have given a freedom of accessing of drain, source, and gate. At the same time, there was one more terminal called sense terminal. So sense terminal, so you can make it work like, if you want to make it work like a JFET, you simply make use of D, SE, and S, and you short these two terminals. So then it's going to act like a normally on JFET. So this is what has been shown here. It's getting shorted and it's acting like normally on JFET. And this is the normally off JFET where your MOSFET itself acts like a gate driver. So that's a very aggressive gate driver, and that was resulting in a very huge amount of EMIs. So the normally off, that is the cascode configuration. I'm not saying about normally off JFET, but if you are making use it like normally off device, then there is a huge amount of EMI. And then we work with some kind of gate drive circuits, and uh, with there may be two approaches. We can make use of voltage source based gate driver. We can make use of the current source gate driver. With the voltage source gate driver, we have to ensure that the negative voltage is to be supplied to this JFET to keep it off. So VGS should be negative. So you need some VGS with negative voltage. But with the current source, what is required, that the current, if this switch is open, the current actually flows from source to gate. So that means the source terminal is sitting at higher potential than your gate terminal. So indirectly you are providing a negative bias over here. So normally on JFET can be controlled both the ways. We tried with both of them with the voltage source gate driver. So we tried with some arrangement, but important thing was placing a negative supply here. So that was very much required. Then we also tried with current source gate driver. So this is one type of a current source. Generally, what happens is when we say about something about current source, immediately the inductor comes in our mind, that there must be an inductor. But find it, the current source which analog electronics people are making use of, they are not nowhere using the inductors. Everywhere they are making use of some kind of switches. So they are making use of these devices such that they start acting like a current source. So we made use of some Wilson current mirrors, So we were able to control, if we control the current in this path, the current in this path is automatically being controlled. So that was the beauty of this type of structure. Okay, so this is some text about it. And then we also try to integrate the protection of the gate driver. So some additional, if there is a, because the problem was that if your supply is getting lost, you gate the source, there is zero supply. It implies that immediately the device will act like a short circuit. So we have to ensure that even if the supply is going out, there should be something that should take care of the flow of current. So we made some protection circuit in it, and then we embedded the two ideas together in this patent. So where we have both the stages, that is the gate driver stage, and as well as the protection stage. Then we tested it for high temperature. That's what I mentioned earlier, that we're working with some HEVs. So the idea was that high temperature testing must be done because we are making use of the radiators as a heat sink. So these boost converters, we place some kind of peltiers, which are basically heat sinks. With a opposite concept. So something gets heated up when current flows through a resistor, that we know, but we can also cool it down by making use of peltier. So that is what we have done. We try to maintain the temperature constant, and somewhere this is our SiC device that we placed on the same heat sink. And the purpose of this unit was to maintain temperature at 100 degrees Celsius. So we tried with boost converter, and we did the testing, but not much difference we were able to get. This is again a simple device. So the idea was to compare them together. First, make sure that theoretically whatever has been claimed, we need to check it in practicals also. So we tried to compare these two, and there was some kind of calorimeter arrangement. We are not relying on uh, these power analyzers. Rather, we are just relying on calorimeter, which was based on heating principle. So with the power analyzer, the issue is some of the harmonics can be they filter out those harmonic terms. So the numbers are not very correct. So the calorimeter was considered as a better one. So the difference was not so much. Yeah, but we choose the similar type of devices. This is very important, that the values of these devices are nearly same, except the voltage across the drain and source. So this voltage rating was different, but the rest of the things were nearly the same. So we tested it for a boost converter, and we find that if we are making use of the JFET, then certainly we have huge gain. If we can operate it at a larger power rating, even if we are keeping the junction temperature constant, because uh, getting the information about internal junction temperature is not an easy task. You cannot place thermal sensor over there, because such a tiny thing. So we have to go ahead with the estimation. So we did some power loss estimation, and then we thought that let's keep the case temperature at the same level in both the cases, and then try to compare. So the green ones are for the silicon, and the blue ones are for the SiC. So you can see the amount of not blue one, or not all of them. This is actually CoolMOS. Sorry about it. This is CoolMOS. So this is blue one is CoolMOS, and this blue here is JFET, and this green one is CoolMOS, and this green is again JFET. So this is our JFET area. So we can take it to a higher junction temperature. At the same time, we can get more amount of power being dissipated through this particular device. So we got some good results, that switching losses were considerably reduced, and power was getting dissipated by the transistor easily. Comparatively, the heating was not so much. So that was a good thing. We further took it to the next stage, that was DC to AC inverters. So the idea was to emulate it just like electric vehicles. So we made use of a permanent magnet synchronous motor drive unit, and this is the control, self-control mode. So by sensing the position, we can control the switching of these these devices such that it's strictly trying to get locked with the magnets, and then it's working well. So yeah, in this case we also try to get the values using this Yokogawa make power meters. uh, yeah, there were some issues in respect of the switching noise. Now this was actually coming because in the case of motor drive application, between two adjacent windings, we have got some capacitance. That's what we call as the interwinding capacitance. So that interwinding capacitance was visible in this case, and that was creating problem. So this is just a figure. In later cases, we made use of this heat sink, and we were making use of some kind of this metal casing, just to avoid that there is some EMI and radiated EMI effects. And these are the devices which we directly pasted onto the hot plate. So this is sitting at 100 degrees Celsius, and we are making use of the hot plates. This is one schematic, and purposely we place these devices over here because we are trying to put it on the hot plate. So that was designed like that. These were few of the experimental results as a function of switching frequency. You can see that if you are increasing the switching frequency, certainly you are getting some improvement in the nature of these ripple currents. But if you're jumping from 19 to 38 kilohertz, there is not much difference that is getting reflected. So in motor drive application, it is okay that even if you go up to 20 kilohertz, you are okay. It's fine. You don't need to take it to a very high switching frequency. For boost converters, certainly that is required, but not for inverter. Then we also try to look into the inverter power losses and the THD, and as a function of load current and switching frequencies, we got much difference. This is what is happening at 38 kilohertz because the switching losses are going up at this frequency. And if you want to keep it cool, better to operate it at low switching frequency. At the same time, your THD was getting improved. It was getting improved much at 19 kilohertz and more. But yeah, after some time, the difference was coming down. So that is a function of load current. Then we also try to look into the losses. So we cannot operate these devices beyond, let's say, beyond silicon devices. We cannot take it to SiC level. So inverter power losses were more with the SiC JFETs. And yeah, for THD in the current, there was not much difference because your PMSM itself was acting like a filter. So the inductance of those motor windings, we're trying to filter those components. These were few of the recommended layouts. We thought of proposing, or better, we proposed that your device temperature can be more homogeneous if you are placing the device in this orientation, because if you are not placing it like this, then some of the devices were getting heated up too much. So and at the same time, our gate driver signal should be perpendicular to the flow of current, so these are getting less affected. So yeah, there were few more work. I'll quickly wind up with this one. Currently, in recent days, we have worked with some current source gate drivers, and we have developed this in our lab that is based on inductor-less solution. So this is one work in which we have tried to make use of the same current mirror approach, but earlier it was just meant for sinking the current. Here it is meant for both sourcing the current as well as sinking the current. So both of the possibilities are there. So in this work, we made use of cascode current mirror configuration, and there were a few benefits of it. Its accuracy was quite nice. It is offering larger amount of output impedance. That's good because your Miller capacitance of the MOSFET, when it is getting discharged, this impedance will offer the gate driver will remain much safe. It's not going to get disturbed too much. So yeah, we did some experiments as well, and this was few of the circuits. And this is the gate drive circuit that we designed, and this is just an enhanced view of that proposed gate driver. And we tried to, and this is our MOSFET, the green MOSFET, that is SiC MOSFET. So we drive it by making use of the current source gate driver. So this is the current source gate drivers. So this is our VGS. Though it is a current source driver, but effectively it's going to create voltage across gate and source. Uh, is there some time, or shall I wind up now? I think I am nearly done. So these are some of the positive features broadly that's going to come by if we are saying it's a SiC based converter. And mind it, this paper was published in 1989. So that's what I was emphasizing, that it's not a completely new story. It's sitting there for 33 years or so. Particularly for battery energy storage, this may be quite useful, but at the same time, we have to understand that what level of battery voltage are we talking about? Are we considering very high powered batteries or low powered batteries? Accordingly, we need to think in terms of the better solution, whether it's GAN or it's SiC. So yeah, I think that's it from my side. And if there are some questions, I'll be happy to answer your queries. Okay.
Thank you very much, sir. It was very detailed and I can say wide lecture on many of the areas, and students have got, I think, a lot of exposure. So if any question from any of the participant is there, please ask the question.
I think they are already exhausted.
Good evening, sir.
Yes, please.
I have only one general question. As in last slide, you shared with us that 33 years ago this technology arrived, but still we are using silicon switch. So what is the major reason behind it?
No, actually, the problem was with the manufacturing issues. The technology was not matured enough. So the theoretical ideas were 33 years back, but maturing those ideas and creating the whole of the, shifting the technology to this level, it takes some amount of time. So that is the gap. But the idea was certainly there. That was in theoretical domain.
Okay, sir. So it will take more time to come into market.
I think that they are already there in the market. The only problem is, are we able to exploit their potential or not? Let's say I have already mentioned about the packaging of these devices. So companies are still putting them in the old casing. So if you are going to put the bad package on a good device, there is no meaning of it. It's good for just for a proof of concept. You can do it or make use in your lab prototype. That's okay. But if you're going for commercialization, then you have to have a very specialized type of packaging. So some other companies are certainly doing it. I'm not denying it, but they are slightly more expensive. So that problem is there.
So it means cost is coming main hurdle in the path of this.
Cost in the advanced packaging is certainly a matter of concern.
Okay, sir. Okay. Thank you, sir.
Yeah.
Any other query from any
Sir,
participant?
I have a basic question, sir.
Yes.
Sir, I have a very basic question, sir. Hello,
Yeah.
sir. Actually,
Yes,
sir,
yes.
I have got a very simple question, sir. Actually, in terms of the perception existing in the market, basically whatever energy storage options we have right now, like in terms of lithium, so the dependency goes on China in terms of reserves, I'm asking, sir. So I just want an insight on your point, like whatever the new options are like emerging in terms of energy, like in terms of battery materials. So what is the role of India? Actually, what reserves are having like available in India? What is the exact scenario in India? Can we actually be self-sufficient in the manufacturing of these things, sir? I'm talking in terms of like if you want.
Yeah. On that note, I have some discussion with some some people in DST. So the thing is, lithium ion cannot survive. At least in India, we cannot be going to rely on it. So
Yes, sir.
there are some sodium-based batteries that people are talking about. I'm not exactly able to remember the name of the material, but yeah, there are some alternative solutions which are not as good as lithium ion, but they are going to compete with it, at least from the cost and availability point of view. So that is certainly coming there. Yeah, loads. I think sodium batteries are there. Yeah.
Okay, sir.
Any other query?
Hello. Sir, I have a couple of questions. I mean, just I want to discuss like, I mean, also managing this gap conversion.
Sorry, I'm not able to hear you very clearly.
Hello.
Dr. Shalendra? Yes.
Now it is okay, sir. Hello.
Yeah, the voice issue is there. Yeah, please.
Hello.
Yes, I can hear you. Yes.
Sir, you have discussed one this dual active bridge converter.
Yeah.
Like SiC based or some normal IGBT based this dual active converter is there, but we are finding difficulty to design this leakage inductance. Can you, sir, tell me something about how we can go for designing of this particular element? Because sometimes if we are going for a higher value, then it's going to operate in PCM, and then when, as you have discussed, like we are going to have for soft switching, one voltage level is coming zero, then we are going to positive negative. So how we can choose this leakage inductance value in gap converter?
That's a very tricky question, actually, to be honest. Yeah, we are also struggling with it. The problem what we encountered was it was a kind of load dependent feature that has actually created the problem. I'm not sure. I can mention one thing that from the power transfer expressions, we need to look at the values of your ZVS is directly going to get linked with it. So if you are integrating these zero voltage levels, I think I'm not sure whether you have tried with which type of modulation scheme. We actually tried with the single phase initially, and then we figured out number of problems. So we moved on to the double this phase shift modulation. So once you are able to, because it's kind of shaping the current in your desired way, then only you can maximize the usage or the capability of those magnetics. and honestly, I don't have a single answer for it. But yeah, that design issues we are also encountering, honestly.
And sir, second thing which I want to discuss, the driver circuit for this SiC-based devices. So,
Yeah.
like normally in IGBT, we are having, I mean, as you told, that this technology is very mature for normal silicon-based IGBT, but I mean, technology is not much mature for this SiC. But it's still how we can design a driver circuit for if we are having a device and we want to design. So only component side we have to change or some, because we require some very high speed frequency for this SiC-based devices. So what are the components which we have to take care when we are going to design this driver circuit for SiC?
Look, the biggest problem with these SiC MOSFETs, I can tell you, is their transconductance problem. Okay, so you need to have a gate driver that has very nice rise time and fall time. Okay, so once we say nice rise time and fall time, that means their capability of pushing the peak current should be as high as possible. Only then you are able to push huge amount of current in a very less duration. So let's say the first few gate drivers we tried was able to push around 14 amps of peak current. So that's a big number. But at the same time, you have to look into whether you are able to handle that the amount of EMI these devices are creating in the PCBs. So it's not, you have to make a trade-off where you can safely operate the device as well as you can take the maximum benefit of high switching speeds. So that trade-off, we figured out that by making use of current source gate driver, that was not giving me the least switching loss, but it was trying to optimize the EMI and the losses together. So those problems were less seen in terms of EMI. So it was trying to make a compromise in between the two. But rightly pointed out, the existing gate drivers which are there in the market, they are based on voltage source gate driver. And if you are making use of it, just try to make sure that the output current of these gate drivers are quite high. So that will try to push it more aggressively.
If they can charge this gate capacitance quickly.
Yes, yes.
Thank you, sir. Thank you so much for a very, I mean, this, is the era of these SiC-based devices, and you have discussed variety of, I mean, you have covered many topics which can help to the students as well as guilty members who have joined us. Uh, over to Sanjeev, sir. So please conclude.
Okay, thank you.
Okay. On behalf of MANIT, and my organizing team, Dr. Shailendra and Dr. Mukesh, we are really thankful to you for sparing your valuable time, because it was really hard to sit in the evening after having a long day, exhaustive day.
Yeah.
And you have accepted our invitation and delivered a very nice talk. And hopefully we'll have some physical interaction. Sometimes we'll have some face-to-face discussions. So we'll definitely invite you for our programs. So sincerely thank you, sir, and hope this will continue. We'll be in touch with all of you. Thank you very much, sir.
Sure. Thank you so much. And it's I'm always delighted to interact with so many new people all the time. It's really nice to interact with the students and faculty members. Thank you all. I'll be very obliged if I may be more useful for you. Okay, and we can look for some kind of possible future collaboration in some of the projects,
Sure,
etc. Yeah.
yes. Thank you very much, sir.
Thank you. Thank you.
Okay, sir.
I'm leaving now.
Okay.
Thank you.
Thank you, sir. Okay, good night.
Good night. Good night.
Now, for all the participants, we had this lecture today, and tomorrow we'll be having another discussion from Dr. Shailendra. It is tomorrow is from Dr. Kalpana.
Yes.
Okay.
Let me check.
13th is on by Dr. Kalpana, I hope.
Yes, 13th and 14th.
By professor from IIT Kharagpur.
Okay, Devnath. Deepankar Devnath. Yes.
Yes. So, and the last day we'll be having discussion from Dr. Sanjeev Dwivedi from Denmark. He will be working on hydrogen fuels and he will be discussing all those things. Yesterday we had posted 2 papers. So we expect that the participants might have gone through those 2 papers. And what we'll do, we'll create a team of say 3 or 4 participants together. And later on, because they have to put up some kind of team discussions also. So based on those papers, have you gone through the papers or whatever you have obtained from that paper? What are the problems identified in those papers? What are the solutions given, and what you can say the research gap is still existing in that particular area? Because today you might have seen that the first paper which was presented for storage technologies somewhere 30 years back. So if you just see the electric vehicle, first electric vehicle was invented somewhere in 1874 or something. But due to constraints in the technology and its marketability, it does not mature, or it has not matured till date. So if you find any such kind of paper, and it is very much important when you are going through the literature to see the state of art oldest paper available, and that is the purpose of those 2 papers. So I hope that you'll be going through those 2 papers, discuss those papers amongst yourself, and if possible, prepare your own review, what you have got out of those 2 papers, at least 3-4 points. Tomorrow I'll be sharing you the formats which are given by the ATAL team to prepare the reviews for those papers. And there are certain other formats which are required to be filled by the participants as an effective evaluation procedure. So those formats I'll be sharing. It is actually the part of that link which I have shared already with the mail for the scheme document, but I'll share for this particular FDP. I'll make a title and share it with you. So you can prepare those details, keep it with you, and whenever it will be desired, you can just submit it. One more thing, at the end of this week, there will be one MCQ in the last half an hour, maybe on the Saturday at 9, we will be having that MCQ. So you have to answer it, and it will be on this team platform itself. It will be given to all the participants, and you have to submit it online. And later on, the second part will be done in the next week when you are having a physical meet here. So with this, I hope, Dr. Shailen, do you want to discuss something?
Yes. So first paper, I think we have discussed yesterday, and in second paper we are having as it is more focusing on charging station, which has been, I think, the first today's talk. The first part was the charging station, how we can integrate these on-board, off-board chargers with the vehicle. So that kind of applications we are covering in the second paper. As you know, like if the voltage, battery voltage is varying from, very low level to a very high level. So some of the cars, they are having a battery voltage low, and some of the cars, they are having a very high battery level.
Can you share the paper, Shailendra? Are you able to share the paper?
This was this is the recent paper which has been published in Q1 Journal. Okay, journal, and it is the Journal of Energy Research. Diligent has written this paper, and so this is focusing on integration of multi-voltages, multi-electric vehicle spot-based three-phase photovoltaic charging system, the modern grid distribution with improved electric vehicle charging capability in power plant. So here, if you see the system topology, directly I'm coming to the system configuration. You can find it out how we can integrate this one. So again, the integration of these renewables as well as battery and grid, we are already having these things. But if we see like if one car is having 400 volt and the other car is having 72 volts, so how we'll integrate both the cars or both the battery cars with the chargers at the DC bus of 700. So at this time, we cannot say that this non-isolated bidirectional converter can boost the voltage from 72 volt to 700. So today, as sir has discussed this dual active bridge converter. So the purpose of this dual active bridge converter, it is an isolated converter, as well as it is operating at high frequency. So we can boost this 72 volt to 700 to discharge it, and whenever the charging is required, we can buck this 700 volt to 70 or 42, 48. So this kind of application, all the control as well as how the power flow will take care, what would be the control for DAP converter in this paper we have given here, like this DAP converter as sir had discussed, single pulse width modulation. So here single pulse width modulation we have taken, simple battery current we have sent, and we have compared with the 10 kilohertz triangular wave, because here we have used simple IGBT. We have not gone for the SiC or some other devices which can fire at very high switching frequency. So 10 kilohertz frequency, 10 kilohertz we have taken, and we have drawn the conclusion like for different voltage rating and different battery rating, then this is the operation of that converter which we have during the charging and discharging. Okay, so this way we have used this DAP converter with the grid integration. People are using only for they are having on board and they plug in their vehicle to the single phase socket and they are charging their vehicle. But if you require fast charging for these vehicles, you have to have this DAP converter, and we can charge our vehicle through these DAP converters. And variety of results we have shown. We have this Opal RT based result for different kind of voltage rating and different like operating voltage as well. So please go through this paper, and you will be having some question related to these papers also in MCQ. Okay, whenever we will give this particular, we'll take this particular exam, you will find out some questions from these. So I think, sir, that is enough from today, and we can conclude today's session. Sir, you are muted.